All right, brand new unit, Unit 7. Unit 7 is on exponential functions. And in Section 7.1, this example video, we are going to talk about the basics. We're going to talk about the basics of an exponential function. So make sure you take good notes. First of all, anytime you have growth or decay that multiplies or divides over certain time periods, those particular mathematical situations are modeled extremely well by exponential functions. These two words right here are going to be very, very important in this whole unit: growth and decay. Anytime you talk growth and decay where you multiply or divide, you're going to have an exponential function. The general form of an exponential function is f of x equals ab to the x power. Or if you want to write it, y equals ab to the x power, however you'd like to do that. But the key is the x is our variable. In fact, it is our independent variable. And as always, the y, or the f of x part, this part right here, is our dependent variable. Now, the a value is usually the starting point, or if you're dealing with money, it's usually called the principal. The b value is called the base. It is a constant number. It will always be a constant. B is the base, and x is the independent variable. A and B are usually filled in numbers that have to do somewhat with the problem that you're dealing with. B is a lot of times a percentage. A lot of times the B value is going to be a percentage, which you're going to see lots of examples as we go through this unit. Now, as we have all year long, let's talk about the parent function. Now, exponential functions have lots of parent functions. But the one we're going to talk about is going to be y equals 2 to the x power. In this case, the a value is equal to 1, the b value is equal to 2, and we have the x power. Now, you could also have parent functions that are 3 to the x, or y equals 4 to the x. Those can also be parent functions. But for the basis of this unit and this class, we're just going to use y equals 2 to the x power. Now, what we're going to do is we're going to make a graph of this. So you can see our little t-table. And what I'm going to do is I'm going to pick values for x that start in the negatives for a certain reason. Now, if I put negative 3 in for x, you're going to get 2 to the negative 3 power. And if you would type that in your calculator, you would find out that you get 0.125. If you type negative 2 and you have 2 to the negative 2 power, you'd find out that that's 0.25. If you put in negative 1, you would find out that that's 0.5. If you'd put in 0, you'd find out that's 1. So if I plot those dots on my graph, negative 3, negative 1.25 is there. Negative 2.25 would be about right there. Negative 1 is a half, which is about right there. 1 is at 0, or 0 is at 1, excuse me. And now I'm going to try some positive numbers and put them in as exponents. So if I put a 1 in for x, 2 to the first power is 2. So 1, 2 is on my graph. If I put 2 in there, 2 squared is 4. So 2 is up to 4. If I put 3 in there, I get 2 to the third power, which is 8. So if I put 3 in there, 8. And if I put 4 in there, 2 to the fourth power is 16, and that's off my chart. And so what I have is a graph, people. If I can draw this well, it's going to be hard on this board, but if I can draw this really well, it goes like that. And that is what an exponential graph looks like. It starts low and finishes high. And the thing is, like in this area right here, it goes up rapidly, which is why it's called exponential. Now, the domain of all exponential functions, the domain is x is less, or x is, sorry, excuse me, x is greater than negative infinity and less than positive infinity. Or in other words, x is all real numbers. X is an element of the real number system. However, the range, you notice that our line never goes over 0, the y value. If I would keep going in this direction with my x values and my y values, the y values are going to continually get closer to 0, but never actually reach 0. So therefore, my range is all y values greater than 0. Very important to make note of this unit, what domain and range are. Now, another new word for you. As x goes this way, as x gets smaller and smaller, or in other words, as it approaches negative infinity, y approaches 0. That is called, when it approaches a certain limit, an asymptote. What is an asymptote? Well, the way you define an asymptote is a line that a graph function approaches It's a line that a graph function approaches as x gets very large or very small. Now, in this case, x is going towards negative infinity, therefore y is getting closer to 0. As x is getting very small, it is approaching this line right here that I'm squiggling in red. That's called the asymptote. Oops. That's called the asymptote. That red line. It's on all graphs that are exponential. If you have questions about that, make sure you ask me in class. But otherwise, please pause the video. And I'm going to go on. All right. Now, I'm going to redraw the graph that you just saw. Y equals 2 to the x power. If I redraw that again, it looks something like this. Now, this particular graph has a name. As x approaches infinity, positive infinity, as x is going in that direction, the y values grow rapidly in that direction. This is called, or an example of a graph that's called exponential growth, because it's going up very fast. Now, in order for it to be an exponential growth problem, our equation in the form y equals ab to the x power. First of all, a has to be greater than 0. A has to be a positive number. And the b value has to be bigger than 1. In order for it to be an exponential growth problem, these are your two criteria in your function. Most importantly, b has got to be greater than 1. Now, I'm going to do a different example for you. And this is going to be an example of exponential decay. Y equals 1/2 to the x power. If I make a t-table for this, and I plug some numbers in, for instance, -3, -2, -1, and 0, you would soon find out by typing this in your calculator that I get the numbers 8, 4, 2, and 1. Now, if I would plot these on my graph, -3 is up at 8, -2 is up at 4, -1 is at 2, 0 is at 1. Now, let's put some positive values for x in there. If I put 1 in for x, and have it be my exponent, I would get 0.5. If I would put 2 in for x, I'd get 0.25. And if I'd put 3 in for x, I'd get 0.125. Now, if you notice, these numbers in the y column are the exact opposites of the one that we did for exponential growth. So now, as x approaches positive infinity, my green dots are going to get closer and closer to 0 without touching that 0 line. It's going to look something like that. So as x gets really large, now the y values approach 0. And the 0 line again would be my asymptote. This is an example of an exponential decay, because now as x approaches infinity, the y values are getting smaller. Y gets small. And in order for that to happen, y equals ab to the x power. In order for that to happen, again, the a value has to be bigger than 1, but now the b value is a number between 0 and 1. That's the whole key for it to be a decay problem. And if it's greater than 1, it is a growth problem. That is your exponential basics. And those are the ideas we are going to use this entire unit as we study different problems. If you have further questions, please make sure you ask.